Welcome to 2.2, a video on polynomials, end behavior, intermediate value theorem, and graphing polynomials. I want to remind you what a polynomial is. A polynomial is a function that has a variable. It possibly could be a linear function. This is linear. This is quadratic. This is cubic. Okay. The domain of a polynomial is always all reals because there's no variable in the denominator and there is no square root. And then the range could vary depending on the polynomial, but the domain of all polynomials is all reals. Okay, so what we're going to do is we're going to look at polynomials and what they do. Their zeros, their end behavior, and some other things, and graphing them, sketching graphs using what we find. You have been given a handout in class, and that's what you need to be looking at. You don't have to write everything down because I gave you the handout for some of this in class. So find your handout and continue on with the video. This is the first handout that we have on here. These are power functions, and what we're doing is we are studying end behavior. End behavior means what is this function doing on the ends. So you start in the middle, right, and you're just looking at the ends, to the right, to the left, and seeing what they do. So as the x values move towards positive infinity, the y values are also increasing or going to positive infinity. So one way to write that is this notation. It says as the x values approach positive infinity, then the y values, or remember f of x, in this case, is also approaching positive infinity. Now, as we go to the left, right, as x goes to negative infinity direction, what is y doing? Well, it's increasing. So what we would say is as x approaches negative infinity on the other side, then f of x also approaches positive infinity. So that's the notation for rises on the left and rises on the right. And that's what that means. So if you were looking at this parabola that's upside down, you can see that it falls to the left and falls to the right. So if I'm doing it with this notation, I would say as x approaches positive infinity, well, what's f of x doing? It's falling, right? So it's going to negative infinity. And as x approaches negative infinity, right, it's going to fall to the left. So this is f of x goes to also negative infinity. So as the x does something, the y does something, and that's what that notation means. So here is a cubic, two odd degree polynomials, right? So their ends go opposite ways. So this one, as x approaches positive infinity, what is y doing? Well, as it goes this way, the y is rising. So that means that f of x, the y values, is approaching positive infinity. As x approaches negative infinity, in other words, as we go this way towards that end, the graph is falling. So f of x is going to negative infinity. And you can see right here that these two are going in opposite directions. And in an odd degree, they will both be going in opposite directions. So if you're writing on this one, it's rising on the left and falling on the right. So as I have and notice I'm starting this out the same way every time. As x approaches infinity, what is y doing? And as x approaches negative infinity, there's only two directions. So you do the two directions every time. All right, so I'm looking at my graph and I'm saying as x goes this way, what is y doing? It's falling, so negative infinity. As x approaches negative infinity, what's f of x doing? It's rising, so positive infinity. And that's all that notation means. But you need to be able to write these using this type of notation. Rising, falling, that's Algebra 1 stuff. Now we're to pre-calculus. Okay, so we will draw conclusions from this. If I have a polynomial with an even degree, to the second power to the fourth, and the leading coefficient is positive, if the leading coefficient is positive, then it's going to rise on the left and rise on the right. If it is an even degree, this is for end behavior. What's it doing on the ends? End behavior. If the leading coefficient is negative, right, then it's going to fall on the left and fall on the right. If it is an odd degree polynomial and the leading coefficient is positive, then it's going to fall on the left and rise on the right, just like a cubic. If the leading coefficient is negative, it goes in the opposite direction. It rises on the right and falls on the left. And so that's a conclusion based on here. So looking at this one, number 15, this is a polynomial with an even degree, right? It's a degree 4 polynomial. The highest degree of the polynomial is 4. So that means I look at the even. The leading coefficient is positive. So its end behavior is going to look like this. And we would say as x approaches infinity, it rises to the right. As x approaches negative infinity, it rises to the left. And that's how that works. This is one of my favorite theorems because it totally makes sense, and it's really easy. What this says is if you have a function that crosses the x-axis, so let's look here. We have we're looking at the y values. We're looking at the y values as x moves this way. You can see that the y values of here are positive. The y values down here are negative. The y value here, where it crosses the x-axis, is 0. So you can see that the y values are positive and the y values are negative on either side of a 0. The intermediate value theorem just says if there is a sign change in the y values from positive to negative, there exists a 0 between those 2 points. That's it. So say for instance, I put in 0, 5. I have 1, 3, 2, negative 13, 3, negative 79, and 4 is negative 255. Right? I can see that I'm looking at my y values, and I can see that these are all positive. And then somewhere in here, it changes to negative. So somewhere in this interval, I have a 0. And it's somewhere between 1 and 2. So the intermediate value theorem says somewhere in this interval, 1 to 2, there is a 0. Right? So f of 1 equals 3, which is positive. F of 2 is negative 13, which is negative. And so that means that somewhere in this interval there exists a 0. Okay, do not write this down yet. Unless you just really, really want to, because this is a lot of information and you don't really need this much. So what this has to do with something called multiplicity. And multiplicity just means that if you have a polynomial in a factored form, then if you have any repeated roots, that's called multiplicity. So it says up here, repeated zeros of a polynomial. So for instance, if I have f of x is equal to x minus 3, that's already factored, right, to the first power, then the behavior at the x-axis is that the polynomial is going to cross the x-axis at that 0. So x minus 3 equals 0, so the 0 is at 3, right? And you can see it there. So if it has a multiplicity of 1, it's a cross. Once again, don't write, just look. Okay, you can see here that if when you factor it, it is the same factor to the second power, right? Then it has a multiplicity of 2, is what you would say. So you would have the root still would be 3, but it would have a multiplicity of 2. And what that shows on here is something called a bounce. It's not going to cross the x-axis, it's going to come down to the x-axis and come back up, or sometimes it goes this way. But it doesn't cross, it bounces. So if this is an even power, right, then it's going to, the actual polynomial will bounce there. Okay, keep a. I'm going to give you a summary page, so just look for now and you can write it here in a minute. This one, as you can see, is the same root again. The root is 3, right, at 3. This is not a cross, we call this a wiggle, because it doesn't just go like a cross, went straight across. A wiggle gets there and then kind of meanders and goes up like this. So it still crosses it, it just doesn't do it as quickly. And so this would be like to the third power or to the fifth power. This has a multiplicity of 3, and so we would call this a wiggle. And so the polynomial, if you know what the factors are, you can tell what it does at the x-axis. It's either a cross, bounce, or a wiggle. Okay, so here's the summary page. If you have a factor with a multiplicity of 1, then at that 0, at that place, you're going to have a cross. If you have one with a multiplicity of 2, then you're going to have a bounce. It's going to come to the x-axis and bounce back like this. So it does like this or like this. Now you might wonder, what does it do if it's, like to the fourth? And so it does the same thing, it just bottoms out a little flatter like that. That would be to the fourth. So like a multiplicity of 4 or 6 or whatever, it just it does that. Same deal here, if they have the multiplicity of, say, like 5 or 7 or something like that. When it does this, it really flattens there. So it just flattens more, but it's just more of a wiggle. So this is I don't have it written on here, but this is a wiggle. Multiplicity 3 or odd. So if it's 1, it's a cross, 2, it's a bounce, 3, it's a wiggle. And this is important, so please write this down and try to remember it, and then I'll do an example on the next screen. Okay, so here's how we put all of this together, using the end behavior that we learned and also learning the cross wiggle bounce that we learned with the factors. So we've started off with an example that is already factored. Now, that's awesome when you're doing the cross wiggle bounce, but it's a little not as self-evident to figure out end behavior. So to figure out the end behavior, you need the degree of the polynomial. And that's not too bad. This here is to the first power, this is to the first power, this is the second and the third. When you add 1 plus 1 plus 2 plus 3, 5, 6, 7, this is a 7th degree polynomial. So it is an odd, right? An odd degree. And then further, the leading coefficient is positive. So it's going to rise on the right and decrease or fall to the left. So that tells me my end behavior. There's your end behavior. Okay, so then what we want to do after this is look at our factors and then note the multiplicity. So this first x, right, x is 0, so here's my first factor. It's to the first power, so it's a multiplicity of 1. That's a cross. My next factor is negative 1, right here, negative 1. It also has a multiplicity of 1, so it is a cross. The third factor is negative 2. It has a multiplicity of 2, and that is a bounce. And then the final factor is 3, with a multiplicity of 3, and that's a wiggle. Now, you're not going to get an exact, you're not getting an exact graph, I mean, you can do that on your calculator, but you're going to get, you know, something, at least know what directions things have to be. And it's like a little puzzle putting it all together. So I know for sure that I have a 0 at 0. I mean, I have a factor at 0. I have one at -1. I have one at -2. And I have one at 3. 2, 3. Okay, here's 3. At 3, it was a wiggle. At 0, it's a cross. At -1, it's a cross. At -2, it's a bounce. All right, so that's what it does at the x-axis. Now I'm taking my odd degree. I have an odd degree here, right? So I'm going to start from down here, and I'll do it without marking it. I'll just follow the arrow. So it starts here. It's going to bounce, doesn't cross. Then it crosses here. It crosses here. And then it wiggles and up, ends up. So remember, it started down. So it starts down like this. Down, bounce, cross, cross, wiggle, and up. So that at the ends, it's doing what the behavior is, and so now I'm going to write it. So I start here, a bounce, a cross. Somebody's asking, well, how far up do you go? Well, I don't know. And then a wiggle. It's a sketch. All right? So that's how that works. So in your composition notebook, write this one down. Using the example that you saw on the previous screen, I want you to make a sketch of this polynomial for class, and we will be checking it in class. Please take the time to do this. Don't just watch a video and then check to do, but actually do the problems. It will really help you when you get to class. One last thing, it says find the equation of a third-degree polynomial with the following zeros. Right, so you're kind of working this backwards. You're going to take the function, and you're going to write the factors. So if it's -2, this is x plus 2 with a multiplicity of 2. And then if it's 4, it'll be x minus 4 to the multiplicity of 1. And here's your equation. Now you can multiply it out if you want, but this is basically it. So it's a third-degree polynomial, right? This is to the first. That's 2 plus 1 is 3, and that tells you. The other thing about some factors come in pairs, and if it's an I function or this, it goes back to the quadratic formula, -b plus or minus the square root b squared minus 4ac all over 2a. And you see this plus or minus? That means there are two roots, right? So if this part, the determinant, is negative under the radical, then you're going to get an I. If it's not a perfect square, then you're going to get one that looks like this right here. So, but that plus or minus means there's two of them. So if it's 3i, its conjugate is going to be -3i. If you have 1 plus the square root of 2, the conjugate is 1 minus the square root of 2. If I have 1 plus 3i, the conjugate is going to be 1 minus 3i. If I have 7 minus the square root of 5, the conjugate is going to be 7 plus the square root of 5. So it's always the middle sign that changes. If I had -5 plus 2 square root of 3, the conjugate would be -5 minus 2 square root of 3. So it's always that middle sign that changes, and that's because of this. That plus or minus goes between and not on the outside. So finding the conjugates is pretty easy, and we'll have some assignments in class for you to practice these problems. See you then.